numbers online school. Today we're going through some problems from the East African Mathematical Olympiad 2025, and the problem is as follows. Suppose that a, b, and c are integers such that a squared plus b squared equals c squared. Show that the product abc is divisible by 60. So the pairs of integers which satisfy this condition are known as Pythagorean triples, and here are an examples of some of them. So we have 3, 4, 5 equals 9, which is 3 squared, plus 16, which is 4 squared, is equal to 25 squared. The same applies to these other pairs. They tend to satisfy that equation over there. So the question is that to show that the product, when you take the product of 3, 4, and 5, then it will always be a multiple of 60. In these cases, we see that this product is obviously 60, so it is divisible by 60. And this product is also divisible by 60 because here we have a 5, and this one here is divisible by both 3 and 4. So in this case, this product has to be a multiple of 60, and likewise here, this multiple of 5 and 4, this multiple of 3, so the product has to be a multiple of 60, simply because 60 is equal to 4 times 3 times 5. So in this case, if a number is divisible by 4, by 3, and by 5, then it has to be a multiple of 60 because these three numbers are actually relatively prime. So how do we prove this? Well, we are going to need modular arithmetic, because when we are dealing with squares, if an integer, if you look at any positive integer, then the possible residues of x, when you look at modulo 3, then we will have either 1 or 0 or 2. That is the remainders when you divide x by 3. And in this case, this means that if you square x, then the possible remainders are 0. When you square 1, you get 1 squared. And when you square 4, you square 2, you get 4, which is actually just 1 modulo 3. So we are dealing with modulo 3. So in this case, the possible remainders of x squared for any positive integer x is either 0 or 1 modulo 3. Okay, let's look at 4. So the squares, the remainders of a number modulo 8 are 0, 1, 2, 3, 4, 5, 6, and 7. Modulo 8. So these are the possible remainders of any positive integer modulo 8. So in this case, the squares will be congruent to 1, to 0, 1, 4. 3 squared is 9, so it's congruent to 1 modulo 8. 4 squared is 16, which is 0 modulo 8. 5 squared is 25, which also is 1 modulo 8. And 6 squared is 4 modulo 8. And 7 squared is 1 modulo 8. So all the perfect squares will leave a remainder of either 0, 1, or 4 modulo 8. Like that. So in this case, there are only 3 possible remainders of perfect squares, modulo 8. And finally, we're going to look at modulo 5. The remainders of any integer, modulo 5, is 0, 1, 2, 3, and 4. Modulo 5. So the perfect squares will be congruent to 0, 1, 4, and 9 is congruent to 4 modulo 5, and 16 is congruent to 0 modulo 5. So these are all the possible remainders of a perfect square modulo 5. And so now when you go back to the problem, if we assume that neither of a, b, or c is divisible by 3, and then because you know the perfect squares leave a remainder of 0 or 1, then if neither of them is divisible by 3, then they all have to leave a remainder of 1 modulo 3. But this will imply that c squared equals to b squared plus a squared. Now b squared and a squared, they are not multiples of 3, so the squares will be congruent to 1 modulo 3, but this is the same as 2 modulo 3. But remember, c squared is also perfect squared, so it has to leave a remainder of either 0 or 1. But 2 is what we get, and we know that 2 is not a perfect square residue modulo 3. So this case is impossible, and we have to declare that 3 has to divide A, B, C. So at least one of A, B, or C has to be a multiple of 3. And so for the case of 8, we have perfect squares are congruent to 0, 1, or 4 modulo 8. So in this case, if some two of the numbers, maybe A and B, are both even, then we know for sure that the product will be a multiple of 4, and there is not much work to do. But if at most one of them is even, so for example, if C is even, or if A is even, or if B is even, and the other ones are odd, then what we get is that the squares of the other ones will be the squares of the odd numbers will be congruent to 1 modulo 8. Because if a square is congruent to 4 or 0 modulo 8, then it has to be an even number. So some two of them will have to be congruent to 1 modulo 8, and the other ones, and the third one will either be 0 or 4 modulo 8. So if we try to do a little casework, for example, if A and B are congruent to are the odd ones, then we get that C squared is A squared plus B squared, which is congruent to 1 plus 1 congruent to 2 modulo 8. But this is not a square modulo 8 because 2 is not present in this set. Okay, but what if A and C are the ones which are odd and B is even? In that case, we get that B squared is equal to C squared minus A squared, and A squared and B squared are congruent to both of them are congruent to 1 because they are both odd. So this is 1 plus 1, sorry, 1 minus 1, which is 0 modulo 8. So B squared is congruent to 0 modulo 8. In other words, 8 has to divide B squared. And in this case, we see that since B is an even number, if B is not divisible by 4, then the square of B cannot be a multiple of 8. For instance, if B is 2 times M, where M is an odd number, then B squared will be equal to 4 times M squared. So 8 cannot divide this number because M is odd, and the highest power of 2 dividing B squared will be equal to 4. In this case, 8 will not divide B squared. So B has to be a multiple of 4, not just an even number. And in the case where A is even and B and C are odd, it's very similar to what we just did here. We just swap the rows of A and B. So in this case, we are done showing that 4 always divides this multiple here, which is ABC. So 4 divides the product ABC. So how about 5? For the squares of 5, we have already seen that there is 0, there is 1, and there is 4 modulo 5. So in this case, what you get from this equation is that if we try to assume that neither of them is a multiple of 5, so A squared, B squared, and C squared will be congruent to either 1 or 4 modulo 5. In this case, again, you can try to do a little casework. If we assume that A square and B square are both congruent to 1 modulo 5, then C squared will be equal to A squared plus B squared, which is congruent to 1 plus 1, which is congruent to 2, and all this is done in modulo 5, which is a contradiction because 2 is not a square. It's not a square modulo 5, but we have seen that this implies that C square is congruent to 2 modulo 5. So this case is impossible. If A and B are both congruent to A square and B square congruent to 1, then this is impossible. How about if A how about if um, one of them among A and B is congruent to 1 and the other one is congruent to 4 modulo 5. In that case, we have C squared is congruent to A is equal to A squared plus B squared, which is congruent to, now one of them is 1 modulo 5 and the other one is 4 modulo 5. In this case, we get 5 modulo 5, which is actually 0, the same as 0 modulo 5. So in this case, we see that 5 divide C squared. Now, because 5 is a prime number, we see that 5 necessarily has to divide C. And consequentially, 5 will divide the product. Now, in the case where both A and B are congruent to 4 modulo 5, then we get C squared is A squared plus B squared, which is congruent to 4 plus 4 modulo 5. But 4 plus 4 modulo 5 is 8, which is the same as 3 modulo 5. And again, this is a contradiction because we know that 3 is not a perfect square modulo 5. In this case is impossible. So one way or another, we have managed to show that 5 has to divide the product of A, B, and C. In this case, we have shown that 3 divides the product, 4 divides the product, and 5 divides the product. So we have these 3 results, the second, and the third, which together have to imply that their product 3 times 4 times 5 has to divide the product, which is ABC. And this is simply because 3, 4, and 5 are relatively prime to one another. So that will be the solution to this problem. And thank you for watching.